Hey everyone, thanks for tuning in today to watch the automated solar harvesting system for vertical surfaces presentation. Our team is RMG Engineering. Our project mentors are Dr. Gao and Dr. Kao, and our sponsor is CPS Energy. Presenting with me today are my team members Kurt Johnson, Jens Knudsen, Osio Blake Cantu, and of course myself, Josue Cardenas. The purpose of this project is to develop an efficient solar harvesting system for vertical applications in order to help reduce the day-to-day greenhouse gas emissions. The project objectives as they relate to the project require us to integrate a pneumatic solar harvesting tracking system into a facade-based array design, optimize the pattern to maximize energy output, and develop a pressure delivery system so that we can control all 12 trackers with a single controller. The performance specifications relate to the environmental survivability, the operation, frame requirements, safety, pneumatics, and electrical components of the system. Guiding you through the design of the project will be Jens Knudsen.
Hello everyone, we're going to go ahead and talk about the design now. Now the first thing we're going to talk about in the design of this array is the solar tracking modules themselves. These solar tracking modules are made up of 3 soft pneumatic actuators, and these actuators are sandwiched between 2 plates. As these actuators inflate, it allows for different angles to be achieved, and this is how we get our solar tracking. Now, with these particular actuators and the pressure we're using, we get a total vertical movement range of 57 degrees and an east-west range of motion plus or minus 23 degrees from the neutral position. Next, we'll talk about the actual whole array. So this array is an 8-foot by 4-foot array, and it has 12 of these modules on it. These modules are specifically spaced based on a MATLAB code, and this code allowed for us to come up with an optimal design and spacing. If you look at the chart that we have, you'll see that our optimized design does indeed perform better than an array that just has maximum crowded panels on it. Additionally, we also get less of a energy dip in the summer months due to summer shading, so you get more consistent power output over the course of the year. I'm going to go ahead and turn this over now to Blake, and he's going to tell you about the pneumatic delivery system and the fabrication of our whole array.
So as my colleague Jens Knudsen just finished outlining the final design of our project and what it entailed, I'm going to dive a little closer into our operating system. Our team developed a pressure delivery system that operated on a slim operating pressure of 9 psi to be able to achieve the tracking capabilities needed by our tracking assemblies. The pressure supply is sectioned independently via means of solenoids, pressure controllers, and regulators, so that in the event of a leak, the remaining rows can continue operation in the effort of continued solar harvesting. Ultimately, our tracking assemblies and its operating system provided an advantage over mechanical systems that required stringent maintenance and replacement cost. Diving deeper into our fabrication processes and what they needed, in the effort of minimizing cost, we were able to leverage commercial off-the-shelf products that required minimal post-manufacturing, whereas the only custom manufactured parts needed for our design were our tracking module components, composed of a material 6061 aluminum in the effort of weight. To the heart and soul of our project, our actuators are composed of a strong hyperelastic silicon composite, which ultimately allowed to support the weight of our solar panels and concurrently meet the environmental specifications outlined earlier. At this point, I'm going to go ahead and pass it off to my colleague Kurt Johnson to talk a little about the rest of our project.
Thank you, Blake. So I'm going to go into our array's test plan So in order to verify that our product met our performance specifications that we outlined earlier, we performed a test plan consisting of 11 tests that evaluated the system's abilities in environmental survivability, performance, and the safety features. So one of our main tests that I would like to highlight is a complete array test that was performed to test the power generation capabilities of the system. After performing this test, we discovered that our array produced an average of 69 watts while consuming an average of 1 watt, meaning that our array performed as expected, and there were only a few minor areas for improvement. So moving on to our program management over here, our project is 100% complete, and at the end of the project, our estimated cost was $3,250 of a $5,000 budget, and our estimated labor cost was $70,000. And in conclusion, the prototype for the soft robotic solar tracking system for vertical applications has a high ratio of power production to consumption, and is an efficient means of harvesting solar power from vertical surfaces. Vertically mounted robotic solar arrays are an exciting area of future study to reduce net building carbon emissions. And with that, we'd like to conclude our presentation, and thank you for your time.